problem 8, and this one is about finding the volume of a solid from its shadow. So that's going to be quite an interesting problem here. So a solid has the following properties. When illuminated by rays parallel to the z-axis, its shadow is a circular disk. And if the rays are parallel to the y-axis, its shadow is a square. And if the rays are parallel to the x-axis, its shadow is an isosceles triangle. So this is basically going from the top, you're going to have a circle. From the side, you're going to have a square. And then from the x-axis, so going into the page like that, you're going to have a triangle. So now the question is, what shape is this? That's quite fascinating. All right, in exercise 44 in section 12.1 of my calculus book, you were asked to describe and sketch an example of such a solid, but there are many such solids, and I didn't actually do a video on this, but there are many such solids, so in this case, we're going to pick one that has a specific length. So assume the projection onto the xz plane is a square whose sides have length 1. All right, and here's the question here, just copy and paste it from my calculus book. So again, describe and sketch a solid with the following properties, and so on. Illuminated parallel is a circle, on the z-axis circle, y-axis square, and x-axis isosceles triangle. All right, so we're going to assume that the xz plane is a square whose sides have length 1. So then we can find a specific shape like this. So part A, what is the volume of the largest such solid? So instead of just any one of them, we're going to pick the largest solid. And part B, is there a smallest volume? All right, so let's take a look at part A first. So solution to A, let's first draw our shadows just to illustrate this. Yeah, so let's draw this out. So let's draw our Z. This is our Y, this is our Z, and this is our x-axis like here. X-axis like that. And let's say we are going downward parallel to the Z-axis or up. But let's just go downwards right here. So if we go down on this object, we're going to get a circle shadow like this. All right. And now if we go parallel to the y-axis, so let's go from here to here, we're shining light from there, we're going to get a square. The square like this. And yeah, we're going to get a square like that. And if we go parallel to the x-axis, we'll make it a bit better. Like this, we're going to get an isosceles triangle. Like this. And yeah, you could shade this in. Alright, and since we're asked to find the largest such solid, so we have this shape, and so the largest possible solid with these shadows is achieved by starting with a cylinder with a circular cylinder of diameter 1 with axis, the z-axis, and with a height of 1. Yeah, or with the axis being the z-axis and with a height of 1. And this is the largest solid that creates a square shadow with a side length 1 in the y direction and a circular disk shadow in the z direction. And to draw this for convenience, we place the base of the cylinder on the xy plane so that it intersects the x and y axes at plus or minus 1/2. So in other words, what I'll draw is let's draw this solid. So we start off with the largest solid. Just first off, start off like this. So here is our z, and now we're gonna have a circular cylinder like this. And it's going to go down like this. So then the base is at the origin. And let's go all the way down across here. It goes down to the origin. This goes around like this. Okay, this goes like that. And then this is the Y. This is the X. And now this is around like that. So that goes around like that. And we're given that the height is 1, so it makes a square, the height is 1. So at this top part, it's 1. And then this is 1 because we're putting it at the origin in the center. So that's 1/2. This is going to be 1/2. And then backwards going to go, etc. Accordingly. But anyways, that's a bit of interesting shape. I didn't draw it exactly perfectly. But anyways, so if you shine a light on it this way, from the y-axis. I'll draw so I didn't draw the y-axis perfectly on it, so we'll just go y-axis like this. We're going to get a square shadow. This is a perfectly, from looking at it from one side, all you see is this. All you see is a square. So you're going to get a square shadow. Like this. So it's square shadow height of 1, 1. So we're going to basically, projection on the XZ plane is a square whose side lengths have 1. Yeah, so in other words, the X and Z plane, you're going to get 1 right here. So this is 1, 1, 1, 1, like that. So just a perfect square. 1. I'll just go, you could do that. We could just do all of them. It's just a square. So that's what we have. And also going downwards, we have a circle. So if you point down here, well, it's a circle, and well, it's a cylinder. So you're obviously going to get a circle underneath there. Like that. Shadow, like that. All right, and then we then remove as little as possible from the solid that leaves an isosceles triangle shadow in the X direction. So we want to make a triangle on this side right here. So this is achieved by cutting the solid with planes parallel to the x-axis that intersects the z-axis at 1 and the y-axis at plus or minus negative 1/2, as in the figure below. Yeah, so in other words, what we want is, so here's our shape. Let's just draw, this is our cylinder. So what we want to do is cut this, and I'll use a different color. I'll draw this in red. So let's say we have a red plane like this. We're going to cut it, that cuts straight through at the edges like that. And it's going to be this on the other side. And this goes all the way also at the bottom there. Like this. So then we're going to cut that and then basically remove all of this extra piece there. So what we end up having is, I'll close this. We get a shape that looks like this. It looks like a wedge. So it's going to be like this. And I'll draw it like this. It's going to be cut off, sliced off all the way. And here you're going to be slicing off less than the top one. You're going to have sliced off bigger edge there. And then it goes, and then this part's going to be just like this, sideways. So you're looking at a 3D. And this is going to be in a circular setup there, like this. So it's going to look something like this shape, or I'll make it a bit more. Like that. Or here I just fix that up. So this basically, we cut it, turns out like this. And this is our z-axis like that. And this goes down, etc. all the way in there somewhere. And like this. And then, again, not to scale. I'll use the solution manual photo soon just to make it a bit better. And that, and this is going to be, this is the y-axis, like this is 1/2. So that when you're shining light this way, parallel to the x-axis, you're going to get a triangle. Looks like a triangle in the back, an isosceles triangle. Shadow there. Here, I just made it a bit bigger, so makes it just in the back like this. Alright, and here is the solid. I just copy and paste from the solution manual here, so it looks much better than my drawing. And it's taller, and so on. Except, except my drawing might have it a bit more to scale, because this one's going to be it looks a bit taller than it is thinner. But anyways, I guess it might be a rectangle on the other side here. Looks like a rectangle shape. But anyways, just imagine it being a square. So to compute the volume of this solid, we can take vertical slices parallel to the XZ plane. So if we were cut this all up like this and cut it up all the way across there and so on, and what we end up having is a shape or a bunch of slices like this. And basically we're going to calculate each volume of each slice infinitely small and then sum it up using an integral. Alright, then going further, so the equation of the base of the solid is the circle with radius 1/2. So basically the bottom is just a circle. Just the radius is just is 1/2 or 0.5. So we can use that. So thus we can obtain the length of the cross. The length of a cross section. So we can know the length of it because we know the equation. Yeah, so we can find out the length of it. Then take an infinitely small section here. We can determine the length using just the equation of a circle, and then so that's we can obtain the length of the cross section of the solid to the right of the origin. So we'll look at to the right of it. We'll look at this semicircle segment over there. And then from here, we also know the height of this. We can also calculate the height of this. This is just going to be as a function because it'd be a horizontal. If you look at it from this way, this is z, this is the y. You can find an equation. This is just a straight up line there. So you can find an equation of z in terms of y. So we'll see how this all plays out. And yeah, I wrote that right here. So we can also obtain the height as a function of y, and thus the area of the cross section. All right, so the equation of a circle, let's take a look at the xy circle. So x plus x squared plus y squared is going to equal to the radius. And we know the radius here, so we're going to just graph this circle right here. That's xy plane, and then the radius is 1/2. So it's going to be 1/2 squared. So in other words, this equals to 1/4. All right, so we have this equation, but what we want to deal with is, well, we'll just make this as a function of y. So what we're going to do is write this as, because we're going to be graphing it on this side. So on to the right of the origin. So that's going to be on the positive y-axis. So what I'm going to do is I'm going to rearrange this so that x, so just solve for x. So x is going to equal to plus or minus, and then move this over to the other side and then square it all. It's going to be square root. Yeah, I mean square root also 1/4 minus y squared, and we only want to deal with just a positive for now. So we're only dealing with a positive value. So we'll just make it positive like this. So x is like this plus, and this is 4. I'll just leave the plus like that. Or actually, I'll keep the plus in there just so we'll keep the plus in there just so that we're dealing with one side of it for everything positive. This is going to be 4y is less than or equal to 1/2, and this is going to be greater than or equal to or 0. From 0 all the way to 1/2, and that's because when you put 1/2, you're going to get 0. And when you put in when you put y is 1/2, it goes to 0. And if you put it more than 1/2, you're going to get a negative value. In other words, we're going to be dealing with imaginary numbers. And if you put this y, if you have it less than 0, you're going to have another scenario. This is going to be positive. It's going to be the same thing as this. You're not going to have a one-to-one function. So again, I just mouthful there. So let's just graph this out. All right, so I'm going to graph this out actually in 3D, just so it makes more. Actually, yeah, I'll graph it out in 3D. Or instead of 3D, I'll just do it like this. I'll put the x positive here. This is the y positive, just so that this lines up with this right there. And then what we'll have is when y is 0. So when y is 0, we're just going to get 1/square root 1/4. So in other words, we're going to get 2, 1/2. So this is at 1/2 right here. This is 1/2 is at 0. And then when y is 1/2, x is 0. So in other words, it goes like this. So we're only going to graph from here to here. And we're not going to deal with the scenario of negative, because otherwise it's going to go over to this side. We won't have a one-to-one function. No, actually, this won't be a one-to-one function either way. Never mind. So, but nonetheless, the solution manual does it with this way, so that we'll have it just from here to here. And what we can do instead is it's going to be exactly a mirror image. So we just multiply by 2 when we take out the full, when you calculate the full length. When you get the full length there, we just multiply by 2. Like that. So on this side. So we're just dealing with the right of the origin, and then we can multiply the full volume by 2 once we do it all. So we're only dealing with the positive side right here. And we also know that we could turn z as a function of the height as a function of y. And we'll draw this right here. So if you look at it from this side, it's a triangle on that other side. So we'll look at the z. So we're going to graph out, I'm going to graph out z like this. Alright, so z like this, and there's the y, and it's going to be an isosceles triangle like this. So this is the height 1, this goes to 1/2 there, this is z, this is y, and this is going to be our 1. So 1, and remember, it goes over to there to another 1/2 over there. So that is our height there, and so then we can calculate each length right here. So this length right here is going to be, we'll call this, well, first I'll call this is going to be a rise or a run. So it's going to rise by 1 and run by 1/2. So then the slope is just going to be, the equation of the line is just going to be, well, z is equal to the origin, or the initial point, 1, minus, and then it's just going to be y times rise or run. So rise is 1 and divided by 1/2, like this, y. And we're minusing because we're going downwards. So then this goes on top. the 2 goes on top, we're just going to have 1 over 2y, like this. Yeah, so thus what we end up having is, so what I'll do now is I'll draw out a section of it. So we'll take out just a general section. This is going to be our x, this is going to be our z, and it's going to go, we're going to take a slice here. So I will highlight a slice right here. Yeah, so let's just take this slice, for example, and just take that out. So let's say we take it out and we only look at that one, and let's say it's infinitely small thickness. So that means we're going to have a slice like this, and it's going to go at an angle down like this. But it's infinitely small, so this angle doesn't really matter. And it's going to be like this. So there is our infinitely small height, and this is going to go, I'll draw this fully like this. And this y goes through it like that. And this is our y, and I'll move this over. And now here, just quickly fix up how the box looks like, because I had it actually below the as xy plane. So I'm going to make it just on top like that. This is going to be our y, like here. And let's say the 1/2 is all the way here. This is 1/2. And the height is all the way up top here. Actually, we don't have to extend this anymore, because this is going to be a function of z. A function of y anyways. This is just the points we're going to be taking the integral from. It's from 0 to 1/2, and now this is the infinitely small thickness dy, so it's in the direction of d, and now this full width right here, this right here is just 2 times this right here. Yeah, so in other words, if I draw the bottom like this, I'll draw it that's hitting this part right here. So this is our a quarter circle, that's this right here. Here, just fix that up. So that's our quarter circle. I'll just highlight it as well, like that. So, and then the distance from here to here is just x. So this is our x. So then, in other words, this is another x, absolute value sign of x, like that, on that side, just so that, we'll just put an x next, like that, because we're only looking at the positive one, and on the other one is going to be x value as well. So in other words, this is going to be 2x, which equals 2, this right here, 2 times square root 1 over 4, 2 times, let's put this again, 2 times square root 1 over 4 minus y squared, like that. So that's that. And now the height of this is, well, we know that's just, the height is just the z value at whatever y value that is. So in other words, this height is going to equal 2, z equals 2, 1 minus 2y. 1 minus 2y. So there it is. That's what we have. Alright, I just moved it up there. And now this whole cross-section right here, this has an area of, and I'll put an area like this. This area, this cross-section, we'll call it a of y. I guess erase this. Let's move it like, okay, so this is going to be a of y. Yeah, here's fix that up. So a of y, and this area is just going to be equal to, well, the height times it by the width. So in other words, or the width times by the height. So the width is 2 times square root 1 over 4 minus y squared. And now the height is going to be, we'll multiply this all by 1 minus 2y, like that. Alright, so we can, so that's our height. I'll just leave it like this. Actually, I'll box this area, and this is our area. Alright, so we can now solve, we'll now solve the volume of the solid by taking an integral and multiplying by 2 because of symmetry, because right now we're only taking from 0 to 1/2. So in other words, we're only finding the volume of the right side, so we just multiply by 2 to get the total side. So, thus what we have is volume, called V, this equals to 2 times the integral from 0 to 1/2, and this is going to be now, this area, AY, A of y times it by the infinitely small thickness dy. So dy we get a small slice, and then just sum it up using integrals. So this is going to equal 2 times, and now the integral from 0 to 1/2, and now put this whole thing 2 square root 1 over 4 minus y squared, and now we have a 1 minus 2y for the z, and this is dy. Alright, so now we could multiply this inside, so we'll have two integrals. So this ends up equaling 2. So 2 times 2 right here is going to be just a 4. So 4 times it by the integral from 0 to 1/2, and this one's multiplied by 1, so that's just by itself. So square root 1 over 4 minus y squared dy. And now this one multiplied by, in this negative 2y. So that's going to be, now this is going to be 2. And there's going to be another negative 2, so we're just going to have a negative. Yeah, it's a negative 4, 2 times, so this 2 times it by this 4. Well, actually, we'll have a 2 times 2 and then another 2, so it's actually 8. So this is going to be 8, like that. Yeah, so 8, and this is going to be, it's negative, and then there's a y there. So we're going to take the integral from 0 to 1/2 of y square root 1 over 4 minus y squared dy. So we have multiple things like that. Alright, so let's solve these each separately. I'm going to call this 1. Each of these integral 1, so I'll call this 1. And this one right here, I'll call this 2. This one 2. So the first one right here, this is just a semicircle. This is just a circle, a quarter circle actually. The square root 1 over 4 minus y squared. That's exactly what we had here. So in other words, this is a quarter circle. This one is, again, this is x equals square root 1 over 4 minus y squared. So that's just a quarter circle. So I'll just write this as, so 1. This is just going to be the volume right here. V of 1, this equals to, well, quarter circle. 4 times 1 quarter circle. 1 quarter, and then this is a circle. And the radius is just 1/2, because again, that's 1 over 4. This was exactly this one. So that's just 1/2 radius. So in other words, quarter circle of I'll put quarter circle like that. Then this equals to 4 times it by 1 over 4, and the 4's cancel. So we'll just cancel like this. And this area is, again, a circle is just pi r squared, and where r is just equal to 1/2. So that's just going to be 1/2 squared. In other words, we're going to get, well, 1 over 4. Let's put a full follow along just to put it all in. Okay, this is going to be pi times it by 1/2 squared. So this equals to pi over 4, like that. So that is our first volume. So now the second volume, I'll call that 2. Alright, this is just like that. Yeah, so the 2, 1, so we got that volume, so I'll call this V sub 2. And this one here is going to be the 8 there, so I'll just go, this equals 2. And, yeah, so this one is an 8, and I'll just write this whole thing out, because we're going to actually use substitution. So 0 to 1/2, y square root 1 over 4 minus y squared dy. So what we notice here is, looks complicated because we have this y and the outside, there's another one there. But if we have this 1 over 4 minus y squared, if you take the integral of that, this becomes this y squared, this vanishes, this y squared will go to 2y dy. So in other words, what I'm going to do is I'm going to let, and then we can see some cancellations going on. So let u, so we'll use substitution, u equals to 1 over 4 minus y squared. So the reason for this is if we take the du, the derivative, this equals to, well, 1 over 4 vanishes. That's just 0. Now this negative 2 squared is going to be negative. Negative y squared is going to be negative. Put the 2 down. Y, it just has 1 by itself. And then the derivative of y is dy. Like that. So notice what we have is this du replaces dy and y. And this is also, there's an 8 there. So V2, they put the 8 there as well. And this also replaces, again, there's another 2 there. This becomes 4. Yeah, so there's the y dy. There's this part right here. And then we just have to make it into a negative. All right, so this becomes, so then if we plug this inside, we get, we're going to get V2 is equal to, 8 is going to cancel with this. So we're just left with a 4. So we're going to have a 4 integral from 0, or we don't need to put the, I'll just ignore that right now. Actually, I'll keep it in, but I'll put a y equal. So we're going from y, not du. We'll replace it afterwards once we get it all. So from y equals 0 to y equals to 1/2, because we're changing the variable right now. So then this y and dy, and there's a negative now, and there's also a negative sign now. put this negative here. So negative 4, and now the y dy is just turned into a du. So we're just going to have a square root u, because we replaced the u, this 1 over 4 minus y squared, and then du. So replace it all. So now this is just a basic integral right here. All right, so this equals 2, and this equals to just negative 4. And then let's take integral of u, square root u is just going to be, well, add a power to it. So add 2 over 2, because that's 1 over 2. That becomes u 3 over 2. And then put a 2 over 3 like this. So that when you, it's the antiderivative. You take the derivative, 3 over 2 cancels with this, and then subtract the power. So we're just going to get square root u. So that's that. And yeah, so then this is integral from y equals to 0 to y equals 1/2. All right, so now we could plug this back in. So let's just plug in our y again. So this is going to be negative 4, and this is going to be 2 over 3 times it by u is going to be, well, 1 over 4 minus y squared, and then to the power of 3 over 2. And this is from 0. This is from y equals 0, and now we change the variable back to y, so we don't need to write y equals 0, etc. That's obvious. So this is going to be 1 over 2. All right, and now we can start evaluating this. So this is going to equal 2, and I'll just take out this 2. This is going to be negative 8 over 3. So move the 2 out and a 3. So negative 8 over 3. And now this is going to be a giant equation. So when you plug in 1/2 inside, so when you plug this 1/2 inside there, this just vanishes actually. So 1 over 4 minus 1 over 4 is 0. So that's just 0. So in other words, we get 1 over 4 minus 1 over 4. So that's 0. And now we subtract. Now we put a 0 inside there. So that's going to vanish. We're just going to be left with a 1 over 4. 1 over 4 to the power of 3 over 2. Like that. Alright, so let's see what ends up happening. Let's simplify this. This equals to negative 8 over 3. And this is going to be 1 over, this is going to be, let's times this by, so there's a negative, times it by a negative, it cancels to be positive. And now we have 1 over 4, like this, 1 over 4, so times it by 1 over 4. And this is going to be square root, yes, 3 over 2. So this is, looks like an interesting problem right here. This is the same thing as writing this part right here. This just equals to, I'll put this as the same thing as writing 1 over 4 power 1/2 and then to the power of 3. So in other words, this becomes 1 over 2. So square root of 4 is 2. Well, actually, before even doing that, we don't even need to do that part. We can just look at this 8 right there and just rewrite the 8 as a 4. So this equals to 2 times 4. And in other words, 4 is just 1 over 1. I'll also put a 2 over 2 right here. So that's the that's the top part. This 3 times 4, 3 over 2. Now we can just subtract the power. So this is going to be, so we can subtract 4, 2 over 2. So this is bigger, so we'll subtract it from the top. So this one subtract or this one subtract into this one. So we get a 2, and this just vanishes. We're going to get 3 times 4 times, 4, and then this is 1 over 2. So 3 over 2 minus 2 over 2 is 1 over 2. And this one now is equals to 2. So this equals 2 over, well, 3 times 2. Square root 4 is 2. And this cancels. We're really left with 1 over 3. So that's entire integral equals 1 over 3. So yes, epic stuff there. Alright. Alright, so thus, what we have is, volume equals to V1 plus V2, and this equals to, this equals to just the integral. I'll just put the whole thing out. Well, it's equal to 2 times integral. 2 times integral from 0 to 1/2 a y dy, and this equals 2. And here's rearrange our order, so let's put this instead. So 2 times square root, integral from 0 to 1/2 a y dy equals v1 plus v2, and this equals 2. So what is the first equation? Pi over 4. So pi over 4 minus 1 over 3. So this is our volume of the solid, of the largest solid that has those 3 shadows. Epic stuff there. And also, lastly, I just want to add one more. So if you plug this into the calculator, you're going to get roughly 0.45. So in other words, V of the solid is roughly equal to 0.45. So that's epic stuff there. So remember, it's pretty much, if you take a cylinder that has a height 1 and has a radius of 1/2 and so on, you're going to end up, and then remove all the pieces to get it a isosceles triangle, you get it like this. So it's pretty epic stuff. And this makes sense because if you take a look at the square, so that is a shadow, a square on this other axis. So if you look at it from this axis, here's a square, but it's all sides 1. So this is all just 1. So in other words, a full solid that has 1 thickness, if you had it in 3D, that's just going to be 1 times 1 times 1. So in other words, just 1. So 0.45 of it. So you shave off 55% of it. So that's 55% of the solid to get its volume. Of its volume to get this 0.45, roughly there. All right, and now let's do a quick calculation check. And you could use the integral-calculator.com website. You just plug it in. So in our case, we have 4 squared. You can just type in 4 squared, 1 over 4 minus y squared, and then you get, it automatically shows it, presents it in this format. So 4 times 1 over 4, all squared, square root there, minus y squared dy. And you could change a variable, add the integral from 0 to 1/2. So you get this giant equation. This one, we just did a circle, so we didn't have to do any sort of other stuff there. So we know it's a circle, a quarter circle, so we just multiply it by pi r squared, and divided by 4. We cancel those out. We just get pi over 4. But if you use the integral calculator, you get this giant thing with the arc sign and so on. And eventually you can plug it in, and this automatically solves it. This is the indefinite integral. This is a definite one from 0 to 1/2, and that's just pi over 4. That's exactly what we got. And we just bypass it using our brain. It's epic stuff. And this other one, here's another one. You can also share the URL. So this one is for the second one. So this is a V2. This is from 0 to 1/2. You could just write literally 8y. Then you put a multiply sign there. 8y sqrt for square root. 1 over 4 minus y squared. It automatically knows what you're talking about and automatically generates this format, 8y, and then square root 1 over 4 minus y squared dy. You get basically this right here, and exactly what we had, 1 over 4, 8 times 1 over 4 minus y squared, and then all to the power of 3 over 2, and there's 8 over 3. There's exactly what we had over here. Here, 2 over 3, 1 over 4, and this can be 8 inside there. 1 over 4 minus y squared divided to the power of 3 over 2. Then evaluates for you and get pi over 4. Oh no, that's the other one. Whoops. You evaluates for you and you get 1 over 3. Exactly what we had. And basically now if you go pi over 4 minus 1 over 3 using my built-in OneNote calculator, you can just go and solve it. Press space, automatically gets you 0.4520, etc. So we just rounded up to 0.45. So epic stuff there. All right, and now let's just jump over to part B. All right, so part B, we're asked, is there a smallest volume? So just to recap, in part A, we found the largest volume of a solid that has the shadows that form a circle, a square, and an isosceles triangle on their respective axis, where the square has a side length 1. So, but to find the smallest volume, well, we could keep removing from the solid infinitely small. Just keep going on and on as long as the skeleton of the shape is formed. So as long as we have our square, isosceles, triangle, and circle. So technically we don't need an actual volume. We could just keep shaving away. So we could take this material and keep shaving away it until we have all we're left with is a thin, is a tiny thin, like almost 0 volume square, and then a triangle that has then a triangle in the center. And then a triangle in the center here. Let's draw this better. Yeah. Whoops. Yeah, just a triangle like this in the center, isosceles triangle, and also the circle, as long as you have a circle at the bottom. So you could basically remove it all until you have a tiny, super thin, super thin material, 0 volume. So there is actually no lowest volume. So going further here to solution to part B. So there is not a smallest volume, and we can remove portions of the solid from part A to create smaller and smaller volumes as long as we leave the quote skeleton shown in the figure intact, which has no volume at all and is not a solid. Thus we can create solids with arbitrarily small volumes. So yes, basically as long as we have the skeleton there, so we can have basically any amount of material on it. just any kind of thickness as long as it's super, 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 super small. And yeah, we can just do arbitrarily small. It can go even smaller and smaller. So there's no smallest volume. So this is basically the skeleton of it. So imagine you remove all this material, all you're left with is this right here. So we have a thin square there. So we have a thin square, and then on this axis, on the y-axis, on the YZ plane, we have a isosceles triangle like there. Then at the bottom, at the base, we have a circle. Yeah, so we have a circle. And again, these are super, super infinitely small, so it's zero volume. So as long as you have any sort of thickness, and you can go arbitrarily small, so there is no smallest volume. You can keep it going smaller and smaller and smaller, approaching zero. And again, if you flash a light, illuminate light on the bottom like this from the z-axis parallel, you get the circle. You get a circle shadow. Going this way, you get an isosceles triangle, and then going this way or the other way, you get a square. So yes, fascinating stuff there.